There's been several requests for instruction on how to use a multimeter, and I have tried to incorporate those in as I go through my daily life and as I use my multimeter. And today I'm taking a look at my Honda Odyssey. I think it has a parasitic draw. The battery's gone dead a couple times, and at first I thought it was related to a light being left on or a door being left open, but I think there actually is a problem now. And whether there is or isn't, it's a good opportunity for me to show how to use a digital voltmeter, amp meter in an abnormal way. And the reason I have to do it in an abnormal way is because at the moment my amp meter isn't working. So basically, this meter will measure amps. If I take this red lead and I put it here or here, and I can put it in line with my battery and I can check amperage draw. Basically, I can check how much electricity is flowing even when none should be flowing. But I can't do that today because my fuses are blown. I loaned it to someone and they weren't super familiar with how to use it, and so I have some more fuses on the way. However, there is a technique you can use where you can indirectly determine if amperage is flowing, and you do that on DC volts or DC millivolts, and what you're measuring is voltage drop. And it's a little bit confusing, and I'm going to use a couple illustrations to lay out the theory to help you understand it in case you don't, and then I'll get into the application of it. My favorite illustrations for understanding electricity, for those who don't yet fully understand it, is to compare it to water flow. And the one scenario with water that everyone's familiar with is a garden hose. So I'm going to use a garden hose to lay out a few principles. So the first thing you need to understand is that in water flow, you have pressure, volume, and resistance. And in electricity, you have voltage, which corresponds to pressure, amperage, which corresponds to volume, and resistance, which corresponds to resistance. So I want you to imagine that I turn on this garden hose, but I only open the valve a little bit. Water will be flowing through the hose, but it will be a low volume of water. It won't fill up a bucket very quick. That's equivalent to low amperage. I then want you to imagine that I hook up this garden hose to a pressure washer, and I put the red tip in, and a very small streams coming out that could just about cut your hand. That's a high pressure application. That would correspond to high voltage, and high voltage can use your body as a conductor, and that's why you can get electrocuted on high voltage, like you might find at your washer or dryer, but not the low voltage that you find in a battery. Okay, now I want to talk for a few moments about gauges and how they relate to, but are not a perfect comparison to, a digital voltmeter. What confuses a lot of people about using a multimeter compared to using a gauge is that a gauge only has one hole. So you hook up this to a garden hose to read garden hose pressure. You hook up that to a tire to read tire pressure, and you hook that up to a cylinder to read cylinder pressure. But what you don't realize is there's actually two ports here. There's this one which goes to the hose, and there's a second one you don't see that goes to atmospheric pressure. Same with this, same with this. So what you can imagine is that these tools are actually like this tool, where there's actually two leads, but one is always hooked up for you. That's a little bit counterintuitive, but believe me, it works that way. If you didn't compare the pressure in the tire to the pressure in the atmosphere, you wouldn't get a reading at all. Now, when we hook up this to the negative and positive battery post, we read 12 volts because we're hooking this up to ground. Let's just refer to that as atmospheric pressure for the analogy, and we're hooking this up to somewhere else in the system, like inside of a tire, if we continue to use the pressure analogy. Now I want you to imagine that instead of reading electricity or voltage, this multimeter would read pressure. And let's say that there is pressure in this hose because the garden hose is turned on. If I put this to the atmosphere and I put this to the hose, I might read, let's say, 10 psi. But now let's imagine that I hook up both of these to the same garden hose. Well, if there's 10 psi in the garden hose here and 10 psi here, my tool tells me the difference. It takes the one value and subtracts it from the other. That's no different than how this works. This takes one value and subtracts it from atmospheric pressure, or vice versa. Same with this, same with this. So a gauge and a meter are basically always doing a relative measurement. Give me a base value, and I'm going to reference that value as I find a relatable voltage. Okay, so if you have a massive kink in the hose right here, let's just do that, and I measure here and here, you can imagine that there would be a big pressure difference. There might be 20 psi here, but then the kink reduces it to just 10. So if you go from 20 to 10 and you subtract those, the value would be 10. So your multimeter would show you the pressure drop, the amount of pressure which has dropped from one location to another. Now, in garden hoses and in wires, there should be essentially no pressure drop or no voltage drop if there's no kink or restriction. And that is a general rule and a general truth. In fact, in automotive, we basically say that from the positive battery terminal all the way back to something like the fuel pump, there shouldn't be more than 0.2 volts of a voltage drop. So some is allowable, but not very much. Same with the ground side. From the negative battery post all the way back to the fuel pump, there shouldn't be more than 0.2 volt voltage loss or voltage drop. However, there are minimal amounts of voltage that is always lost as electricity travels through a wire. There's always something. Just like there's always a little bit of pressure loss inside of this garden hose. If this garden hose was 1,000,000 miles long, by the time water came out the other end, it would have lost all of its pressure. The volume, the water would still eventually flow, but it would have given up all of its pressure trying to run through this extraordinarily long garden hose. So as the length of the wire increases, or as the diameter of the wire decreases, you'll get larger amounts of voltage drop. Now I'm going to try and show you how that principle relates to the vehicle. Okay, so if I have the vehicle off and asleep and all of that, but I go from the positive battery post to the negative battery post, I get 12.6 volts, which is completely expected. Now, what if I go from the negative battery post here to the negative battery post just a little bit further on? I get 0, and that's expected because I'm taking two measurements right next to each other, and there shouldn't be any voltage loss or voltage drop. Now, if I go from the negative battery post all the way to the engine ground, I also get 0, which is expected. But when I go from the negative battery post to the body ground here, I get 0. That's because I forgot to flip my meter to millivolts, which I meant to do first. I like to show my mistakes sometimes on here to show that I'm human. Okay. When I go from the negative battery post to the ground on the engine, I get 0 millivolts. But when I go to the body ground, all of a sudden I get 0.2. Now, that's not a significant amount of voltage loss. But what it shows you is that there is a difference in voltage from the negative battery post, which is ground, to the body ground, which is also ground. And that corresponds to me taking a measurement at two different areas on the garden hose. And if there's any voltage drop at all, that indicates that the water is flowing through the garden hose. Or, back to the vehicle, if there's any voltage drop at all, that means that there's a small amount of amperage. Now, most vehicles will have an extraordinarily low amount of amperage flowing when they're asleep. Asleep basically means the vehicle's locked, the hood is closed. In this case, I've manually closed the latch so that the car thinks the hood is closed, and all the control modules have gone to sleep for the long nap. The amount of voltage draw, amperage draw on a vehicle will vary, but the standard that we always used at Volkswagen was around 30 to 40 milliamps. But the Touareg and the Phaeton, which were more sophisticated, had 50 to 60 milliamp draw. You'll have to maybe do some of your own research on your own vehicle, depending on how old it is or how new it is. There will always be a little teeny tiny amount of sleep current, and that's so that when the customer walks up with the key, the vehicle is alert and awake and ready to go. It doesn't want to be completely asleep. Okay, so some is normal, but some could become abnormal and drain the battery. Okay, we're getting to the nuts and bolts of how we're actually going to use this. Thanks for sticking with me so far. It's important to understand the theory before you can understand the application. Okay, so I've set up one lead on the negative battery post and one lead on the intake manifold, which is an engine ground. And you can see that right now there is a 0.0 millivolt voltage drop. And that's because there's no amperage flowing through the circuit at all. Now I'm going to take the key and I'm going to unlock it. And you immediately see there's now some voltage drop. The voltage drop essentially correlates to the amount of amperage being flowing through that circuit. Now, when I lock it again, so right now I unlocked it, everything woke up a little bit and it got ready to start the engine because it assumes the customer is approaching the car. So sometimes when you open the driver's door, as an example, the fuel pump will prime, preparing the engine to start, things like that. But right now, probably the engine control module just woke up and now it's deciding, well, maybe I'm going to go back to sleep. Now I'm going to lock it. You saw it just went up to 11. And watch what happens when I honk the horn. 11 again. Interesting. Now, I'm going to take this off of here, and I'm going to put it on the body ground. We're going to do the same experiment. So right now on the body, we have 1.3 millivolts. We're going to unlock it all the way up to 17 there for a moment. We're going to lock it, 25, and we're going to honk the horn, 32. So that 32 millivolt voltage drop across the negative cable going to the body is related to the fact that the horn just activated and the horn drew some amperage. And although the majority of the voltage dropped as the horn consumed that amperage, well, that's not quite the right term. An electrical engineer would correct me there. You still see an increased voltage drop across this cable because of the increased amperage flow. Now, perhaps you've already guessed, but the reason why you can indirectly measure amperage with voltage is because of Ohm's law. Voltage, amperage, and resistance are all connected, and as you change one of the other ones will change in response. Now, if you've ever heard of an amperage shunt, it's a device used by engineers and measurement technology people to measure the amperage in a circuit. And instead of having some huge device in line to measure amperage, what they do is they actually measure the voltage drop across a resistor, which has a known value, and then that voltage drop corresponds to a particular amperage amount. And that's exactly the technique I'm going to demonstrate right now. Now, before I demonstrate it, I want to explain a couple reasons why you might want to use this. Because some of you are probably thinking, yeah, this guy doesn't have an amp meter because he blew the fuse out of it, and now he's come up with this ridiculous way to take measurements. But that's not really true. There's at least two reasons why you might want to know how to do this. The first reason you might want to do this is because as cars become more and more sophisticated, the old technique of removing fuses and waiting for the amperage draw to go away is no longer a viable option. So the classic way to do this would be to hook up my amp meter in between the battery and a cable. So you remove the negative cable, you go from the battery to the cable, and then you get, let's say, 40 milliamps or 400 milliamps. And then you start pulling fuses until the 400 milliamps drops down to 4, and you say, okay, something on that circuit is awake. Here's a problem with that on a more sophisticated vehicle like a Volkswagen. As you start pulling fuses, you might pull a fuse to a module which was communicating with another module. And as soon as you do that and that module goes dead, the module with whom it was communicating wakes up and says, whoa, 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 I just lost the transmission control module. What's going on? And all of a sudden, the vehicle will come out of sleep mode and go into active mode and try to start figuring out what's going on, maybe being able to fix it before the customer returns. Now, what that does for you as the mechanic is it means that in some cases, you'll pull a fuse, the amperage draw will actually go way up, and you have to wait 10 minutes for the vehicle to go back to sleep. And so it becomes extremely cumbersome to do that technique. You still could, but it would require an incredible amount of patience. So when I was at Volkswagen, there was a technique that was shared with us. I'm certain that it's at other manufacturers as well, where you would take these two leads and you would check the voltage drop across the fuse, because you can check the voltage drop across most fuses on the backside without actually removing them. And what you would find, I'll just make up the numbers just to make it simple. What you would find is that little tiny fuses would only drop, let's say, 0.1 milliamps, but all of a sudden one would be dropping 10 milliamps, or 0.1 milliamps. 10 times the amount is what I'm trying to say. And all of a sudden that would give you the hint with a voltmeter without ever disturbing the vehicle that one circuit was way more awake and consuming way more amperage than others. So this technique is useful even if you have all the equipment in the world and you don't have blown fuses. The second reason that this might be useful to you is you cannot always install an amp meter between circuits. So this, you'll see right here, this has a 10 amp maximum. So even if I had a good fuse, if I wanted to check something like radiator fans, which pull more than 10 amps, you can't actually put it in line. It might also be very impractical to put it in line. You may not have the tools to remove the connections. They may not be easily accessible. And you may also find yourself in a situation someday where you don't have an amp meter. Most of the techniques that I'm interested in are the ones that allow you to do more with less. I'm preparing to become a missionary and move overseas. And so I'm always thinking about, well, if I'm in the bush or I'm in the backcountry and I don't have Amazon and all these tools, is there a way for me to get the same job done? And that comes from an old friend of mine who grew up on the island of Sark in England. He grew up without a lot of resources like we might have on the mainland. And by the time I met him in his 20s, he just was extremely adaptable and innovative when it came to solving problems. I absolutely loved and admired that. Okay, so hopefully all of that theory and the basic application of the technique makes sense. I'm not going to take a bunch of measurements on camera because that's pretty boring, but I'm just going to bring you in here for the close shot. So all of these fuses, you can see to the left and the right of the 15 that there's little metal pins, and those are the same pins that go into the fuse, and those allow you to probe and touch and see what you have. And so I'm going to go through all of these and check for any that have more voltage drop than the ones next door. So as an example, if all of these 10 have 0.1 millivolts, but then one has 0.6, then I know that's something worth investigating. Now there is a limitation in this case because all of these have caps. You can't easily get to them. You can pop these caps off. That's a little bit cumbersome. I may end up doing that. So I may still in the end only find this by hooking this up and disconnecting things, but it's still a viable option. An alternative would be to hook up the millivolt voltage drop from the negative battery post to the body, and it was reading about 0.2 before, and then you can start pulling fuses and you wait for that 0.2 to go away. That doesn't tell you how many amps are flowing, but it does give you an indicator when the amperage that was flowing stops flowing. So this is more of an advanced technique for people already used to using voltage and ohms and things like that with their voltmeter, but several of you have requested this type of thing. I thought it was an interesting and worthy topic, and even if you don't ever use this, it may be helpful to know that it exists so that if you're ever in the situation, you might not recall how to do it, but you at least recall that that's something you could go and Google and look up. Never forget, Ohm's law means that all three values, amperage, voltage, and resistance, are related. So sometimes there's more than one way to skin a cat, and you can get one value by taking a look at another value. Take care, folks. God bless. Talk to you later. All right, a little bit of bonus footage. I'd always rather show rather than explain, and I didn't realize this was going to happen, but it did. So the vehicle's asleep. I got a 0.1 millivolt amperage voltage drop across negative battery terminal to body ground. Some quick calculations tell me that could be 100 milliamps all the way to an amp. In any case, 100 milliamps would be too much. So I think I've confirmed their parasitic draw is going on right this moment. Now, the old, pull the fuses and see which one makes the amperage go away. I want to show you what happens when I pull this 40. So you can see I'm at 0.1. I pull it, I go down to 0, which is good and interesting. So I think I may have found something. However, let's say that it didn't make a difference. Watch what happens when I plug it back in. It wakes things back up. And now I have to wait. I've already done this once. I have to wait about 5 minutes for it to go back down. It stays at 0.7 for like the next 5 minutes. So you can see how probing the individual fuses without disturbing anything can really be a time saver. Right now, I'm basically cleaning up the shop while I wait for this to go back asleep. So it's a limitation. That's exactly why this technique is so good. Last thing is, follow the link in the description below. It'll take you to a chart that tells you how many milliamps are running through these different types of fuses when you do a voltage drop across them. That's a super helpful thing. It also shows that everything I've said today is real and legitimate, not just made up, because perhaps you got that impression because I'm so unprofessional. Anyway, have a good one.